Okay, so now let us talk about the integral test for series. Okay, and the integral set, it says like this: if you have a sequence, okay, an with positive terms. Okay. And also, we let this an to be a function type, where the function f is continuous, positive, and decreasing for all x is greater or equal than a capital N. Okay, this capital N is some positive integer. Okay, and then the integral says like this: the series and the integral both converge or both diverge. Okay, so this is the brief integral test. Okay, the idea is as long as the corresponding f function satisfies its continuous, positive, and decreasing, and then to check whether the given series converge or diverge, it's equivalent to check whether the corresponding integral converge or diverge. Okay. And another thing I would like to address is this integral test does not mention anything about if the integral converges and then the sum of the series. Okay, in other words, if you have a problem, you evaluate the corresponding integral, it proves it converges. Let's say it converges to capital M. That capital M has no relationship to the sum of that series. Okay, so only we know that it's the integral converge and then the corresponding series converge. Okay, so now let us start with one example, and very basic example here. Okay, so first one, let's do, if I have this very classical harmonic series, okay, and then you can see that since our an equals 1 over n, so correspondingly the function I have here is going to be 1 over x. And then since my n starting from 1, so I let my x is greater or equal than 1. Okay. So for my function fx here, it's very easy to check that my function, it is continuous, positive, and decreasing. Okay. Often the continuous and positive part are always. The function itself, if it's complex, so to show the decreasing, what we can do here is we can always take the derivative of the given function. Then it's going to give us this negative 1 over x squared. And we know that the derivative is less than 0 for all x greater or equal than 1. So we can guarantee that the corresponding function is decreasing on this interval. So we're good. And then after we get that, starting from part 2, we're starting to evaluate the corresponding interval, which is 1 to infinity 1 over x dx. Now this is an improper integral, so we can write into a limit format, which the antiderivative of 1 over x is ln of x. Okay, and it should be ln of absolute value of x, but since my x is from 1 to b, and so I can actually drop that absolute value sign. So plug in, that's going to be ln b minus ln of 1. Ln of 1 equals 0, so that becomes into ln of b. And as b goes to infinity, ln of b is also infinity. That means this integral does not converge. Hence, based on the integral test, our original series 1 over n also not converge. Okay, so based on the integral test, this series, which we have a name, is called the harmonic series. Actually, it's diverge. Okay, diverge. From here, we can explain a little bit more stuff, which we're going to introduce is here. It's a series called P-series. Okay, so the P-series is in this format. So it's 1 over n to the power of p. Okay, so you can see the n starting from 1 to infinity here. So the P-series is converges when p is greater than 1. Okay, and then diverges when p is less or equal than 1. And apparently, as you can see that when p equals 1, it's a harmonic series, and that is diverge. So the conclusion about the P-series, it is very important for solving a lot of series problems. So hope you can enjoy this video, and thank you for the watching.